As we saw in the previous video and in our previous assignment, the gas laws have several factors that influence them. Those factors are pressure, temperature, and volume. And also, although we don't consider it very much at first, the mass or the number of moles of gas. In the first instances, the mass and number of moles of gas will always be held constant. In the next video, you'll see that they can change, but for now, they're constant. The first law is called Boyle's Law. This was proposed by Robert Boyle in the year 1662, and Boyle proposed that pressure and volume are indirectly proportional to each other. Therefore, the initial pressure and volume of a gas, when multiplied together, will equal the final pressure and volume of a gas when they're multiplied together, and you've changed one, the other one will change also. And if you remember, an indirect relationship means that when one goes up, the other will go down. For example, what is the volume of gas that starts at a pressure of 103 kilopascals and a volume of 5 liters, and the pressure is changed to 85 kilopascals? Since the pressure went down, you can assume that the volume will go up. If we use our standard method of solving problems and write down our variables, pressure 1 is 103 kilopascals, volume 1 is 5 liters. Pressure 2 is 85 kilopascals, and volume 2 is unknown. Plug your values into the equation, leaving your unknown variable as a variable. Rearrange to solve for your unknown, and you get a volume of 6.06 liters for your new volume. And as you can see, the volume went up when the pressure went down. The next factor we're looking at is temperature, and temperature is described by Charles's law. That's Jacques Charles, 1787. He was French. He proposed a direct relationship between temperature and volume when mass and pressure are constant. A direct relationship, remember, means that when one goes up, the other goes up, and when one goes down, the other goes down. That law is expressed as V1 divided by T1 equals V2 divided by T2. So the initial volume divided by the initial temperature will equal the final volume divided by the final temperature. An important thing to note is that Charles's work helped William Thomson, otherwise known as Lord Kelvin, recognize the importance of the temperature negative 273.15 degrees Celsius. That is known as absolute zero, and that is the point when all molecular motion stops. And it is also what the Kelvin scale is based on. And one thing to note is that we always use Kelvin temperatures when we deal with gases. So make sure you always convert to Kelvin from Celsius. So first we have to convert into Kelvin, and you'll see that I did that here. All you do is add 273. If you want to be exact, you can add 273.15, but just add 273 to your Celsius temperature, and that converts your temperature to Kelvin. So 24 degrees Celsius plus 273 is 297 Kelvin, and 58 degrees Celsius plus 273 is 331 Kelvin. So plugging the values that we have identified for each variable into the formula, we get 4 liters divided by 297 Kelvin equals our unknown volume divided by 331 Kelvin. We rearrange to solve for our unknown volume, and we then solve the math, and we get 4.46 liters for the volume of our balloon when it changes from from 24 degrees Celsius to 58 degrees Celsius. So notice the volume increased when the temperature increased. That shows your direct relationship. Our third relationship is with volume, and we have Gay-Lussac's law, which was proposed by Joseph Gay-Lussac in 1802, and he proposed that pressure and temperature are directly proportional when volume and mass of a gas are constant. Again, a direct relationship means that when one increases, the other increases. The example problem we'll use for this is a gas in an aerosol can. The can is under 103 kilopascals of pressure at 25 degrees Celsius. So this is basically room temperature and normal pressure. If this can was thrown into a fire, what is the pressure when it reaches 928 degrees Celsius? So again, we write down all our variables, we plug them into the equation, and we get 103 kilopascals divided by 298 Kelvin equals our unknown pressure divided by 1201 Kelvin. We rearrange and solve for our unknown, and we get 415 kilopascals of pressure. Finally, we combine the gas laws into one simple formula. And notice on the left side of the screen, I have the individual laws, Charles's law, Gay-Lussac's law, and Boyle's law, And if you look at the variables, you'll see that they're all in the same positions. They're just combined with different variables for each law. So what we do is we combine them, and we get this formula. P1 divided by V1, times V1 divided by T1 equals P2 times V2 divided by T2. So your initial pressure times initial volume divided by initial temperature will equal the final pressure times the final volume divided by the final temperature. And that concludes our discussion on gas laws.